Hi everybody, in this video we're going to start discussing some algebraic methods of evaluating limits. Specifically, as this video is called, this one will be all about something called the dividing out technique. The dividing out technique absolutely requires you to harken back to all of your factoring knowledge. So without too much more introduction, let's get started. Let's examine this function right here. We want to evaluate it as x approaches -2. So as always, our first line of defense is always direct substitution. So let's see what happens if we try direct substitution. I'm just going to go right to some of the simplified versions here. So if we plug in x equals -2, we do get 0 over 0. All right? So oftentimes when this 0 over 0 comes up, this signifies what we're going to call a removable discontinuity. In the previous section, in 12.1, we talked about when limits fail to exist, and one of the types of discontinuities that got you to know that a limit failed to exist was an essential discontinuity. There is no essential discontinuity at this point, at x equals -2. And we'll look at the graph in just a second. But there is an essential discontinuity in this function at another location. If you just for a quick second tried to evaluate the limit as x approaches 5 of this same function, you'd actually find an essential discontinuity. And I just want to take a quick second and show you what that looks like numerically. So if you try to evaluate the limit as x approaches 5, you actually get 7 over 0. And that 7 over 0 is going to indicate that you have an essential discontinuity, where this 0 over 0 is going to indicate that you have a removable discontinuity. Now let's look at what that looks like graphically. So graphically, here's the image. And if you look at what's happening around -2, basically the function is pretty nice. There's a nice trend. And hopefully you can see that this thing is approaching whatever this -0.142 value is. For those of you who are really great with fractions, it's -1/7. We'll show that in a few minutes. But what's happening over here at x equals 5? Well, this is where that essential discontinuity comes in. This is that vertical asymptote. So recognizing the numeric values that get you removable versus essential discontinuity is a real important feature. Let's get back to the original limit, though. Let's talk about how to find the limit in this particular thing. And so what you're going to have to do is factor. All right, so what's going to happen is somewhere in this is something that's creating a 0 over 0. So in this particular case, if you factor the denominator, what you're going to get is we need two values that multiply to -10 and add to -3. So what you're going to get is x plus 2, x minus 5. And okay, fine. What happens next? Well, the x plus 2 on the top divides out the x plus 2 on the bottom, leaving only a 1 in the numerator. So now what we have is 1 over x minus 5. And so what we can do is evaluate the same limit we started with, but on this kind of new version of it. So let's take the limit as x approaches -2, but of this kind of new reduced function, 1 over x minus 5. Now we can just drop this thing right in here. -2 minus 5 gives you 1 over -7. That's where that initial decimal came from. And if you're asking me, how does this thing fit into the graph? Well, let's graph it on Desmos and take a look. So I've returned to Desmos here, and I have the function 1 over x minus 5, that reduced version here. And so now we can plug that gap. Basically, this thing lies directly on top of the original function, but it has this x plus 2 eliminated so that x equals negative 2 is defined on this version, this reduced version, this simplified version. This function is identical in every way to the red function, the original one, except the blue function is defined when x is equal to negative 2, where the red one was not. So the key to the dividing out technique is going to be factoring and canceling terms. Hint, the one that makes the 0 on top and bottom is going to be the one you're going to want to divide out. So let's take a look at a couple more examples. I'm going to be doing a lot of suggesting here. For instance, right now, what I want you to do is pause the video and attempt to factor the top and or bottom to find a term that cancels out on both the top and bottom. So hopefully you took a second, tried plugging in x equals negative 3. If you do that, you get this 0 over 0. It indicates a removable discontinuity. Let's cheat a little bit. The x plus 3 is definitely the thing that needs to go away. It creates a 0 in the denominator. So perhaps you can use that to your advantage. X plus 3 is absolutely a factor of the numerator. So hopefully you're able to factor this numerator into x plus 3 times x minus 2. Let's get our pen on right here. And what happens is the x plus 3 in the top and the x plus 3 in the denominator do divide each other out. And you're left with an equivalent function, x minus 2. And the limit of that one is very, very easy to evaluate. The limit as x approaches negative 3 of the function x minus 2 is simply negative 3 minus 2 equals negative 5. Now let's take a look at another. The rest of the videos in this sequence will be similar in nature. We'll want to factor out and cancel some terms. So taking a look at this one, again, trying the direct substitution route. I know that when I plug in x equals 2, the bottom is definitely going to be 0. So what you're going to want to do is try to factor the top and factor the bottom. No, you don't need to factor the bottom. Factor the top, see what happens. In this particular case, I'm thinking you're going to want to factor this thing by parts, pulling out common factors of those two. So why don't you pause the video and see what you can come up with. Hopefully what you came up with is something similar to this. Again, I finished the direct substitution with that 0 over 0, showing that there's definitely a removable discontinuity. Once you look at a common factor of these two terms and these two terms, you got an x squared. X minus 2 is what remains. Take a 3 out of both of these two. So what's nice about this is the x minus 2 matches here and here. We use these two terms to create the other binomial factor. The x minus 2 now divides out top and bottom. And now we have a nice, easy limit to evaluate as x approaches 2 of the function x squared plus 3 is simply 4 plus 3, which is 7. We've got two more. Here's the next one. Again, trying direct substitution is always your first line of defense. 3 to the third power minus 27 over 3 minus 3 definitely gives you 0 over 0. So take a couple minutes, see if you can come up with how to factor the top to get this x minus 3 out of there. There are two distinct ways of factoring this thing. So why don't you pause the video and do that. All right, so I have this thing factored into a way that's going to divide, but I do want to talk about how I factored this thing. First things first is this is the difference of two perfect cubes. If you remember, there's a special factoring pattern, a cubed plus and minus b cubed. And that would be a plus and minus b, a squared minus plus ab plus b squared. This would be the same, opposite, always positive. This is affectionately known as SOAP because that gives a way to remember the signs for that thing. So that's where you can follow the logic, that special factoring pattern. The other way you can do this is actually with synthetic division. Since we know x minus 3 has to be a factor that divides out on both top and bottom, we can use positive 3 as a divisor, because positive 3 would be the root associated with that thing. So go all the way back into the depths of your factoring and synthetic division knowledge. I'm sorry, this would be 3. Adding vertically gets you that 3. Multiplying diagonally gets you the 9 here. Adding vertically, multiplying diagonally. Here's your remainder. And here's your constant, your x, and your x squared term, which definitely matches what we have going on over here. So now that we're here, we can cancel this thing. We can divide out. I don't like the word cancel. So now we have the limit as x approaches 3 of x squared plus 3x plus 9, which we can definitely directly substitute that 3 into to get 9 plus 9 plus another 9 is 27. Finally, got one more problem to look at, and that's this one. Again, when you try direct substitution, you definitely get 1 minus 1 in the denominator to get you a 0. Just confirming on the top, 1 cubed plus 5 times 1 plus 3 times 1 minus 9 definitely gives you a 0 over 0, which is indicative of a removable discontinuity. So try factoring. X minus 1 definitely has to be a factor of the numerator, so try synthetic division like in the previous one. Again, pause the video, check it out. Hopefully you get something like this, where the x minus 1 on the top and the x minus 1 on the bottom cancel out to allow you to evaluate the limit as x approaches 1 of x squared plus 6x plus 9 and get the limit 1 plus 6 plus 9 equals 16. So that is the dividing out technique in a nutshell. Shoot me a message if you need any help with factoring.